Hey everybody, welcome back to the Algebra 2 series. Today we're doing some unique work with trigonometric concepts. So we're going to start with this idea of using four quadrants to show that the cosine of x is equal to the sine of x plus pi over 2. So the first part of this is to talk a little bit just generally about the quadrants. So once again, with the sine function, so if we're dealing with sine, then we know that sine is positive in 1, 2, negative in 3, and 4. And the cosine is positive in 1 and 4 and negative in 2 and 3. So if you could imagine for a moment that the cosine x is some angle, and the angle is in the four quadrants, and if we were to take this grid on the right here and rotate it positive pi over 2, which is 90 degrees, it would take this entire quadrants, all four quadrants, and rotate them to look like that. So the first thing we notice is that the cosine of x and the sine of x plus pi over 2 coincide with their signs, SIGN signs. So that's the first thing to notice. So that's a kind of a cool concept just in itself. But let's just work with this from here on out. So now I'm going to make an angle in the quadrants. So I'm going to make the angle look something like this. Here's my x. That's the angle we're talking about. And we know that whenever we calculate our trig functions, we have a reference triangle drawn. So here's my little reference triangle. I'm going to put a mark for that angle right there, that reference angle. We know, of course, that this short leg is going to be negative because it's in quadrant 2. The opposite side will be positive. Our hypotenuse will always be positive. Now what we're going to do is we're going to take this cute little angle, x, and we're going to rotate it to show this one right over here, x plus pi over 2. So as we rotate it, what's going to happen is the triangle itself is going to rotate exactly 90 degrees. So this angle right here is 90 because we're rotating positive pi over 2. And when we draw a reference triangle, we'll notice that the reference triangle kind of looks like the other one, but it's a little bit of a different orientation. Let me see if I can draw that just a bit better so that we can see the length be the same for our hypotenuse. And notice it is a right triangle because we always create right triangles with the x-axis. Since our hypotenuse is always positive, we'll put that back in there. Notice that this time the long leg is negative and the short leg is also negative. So in doing this, we've kind of changed over a couple of things. So let's look at what has happened here. If we were to calculate in the blue triangle, what is the cosine of that x angle, we would say that it's this short negative value over the hypotenuse, the short leg. And notice that in the other one, it's the same thing, the short opposite and the hypotenuse. But in that case, that's the sine, not the cosine. The opposite is the sine, so that's going to be x. And of course, we're talking about the pi over 2 angle. And you can do this all the way around the circle and convince yourself or prove to yourself that this little relationship that we started with here is true. So that's kind of a neat little way to show that the sine of x plus pi over 2 is equal to the cosine of x. Okay, let's move on and show it a different way. Notice that we could use a graph to show that the sine of this x plus pi over 2 is equal to something. I shouldn't put an equals equals, but it's equal to something, and we're not sure what yet. So we could do it kind of by a semi-discovery method. So we would simply graph the sine of x. It doesn't have to be perfect. It can just be close enough. And we, of course, know that this is pi and this is 2 pi right there. And if we take this sine of x graph, and we know that by transformations, we're talking about a left pi over 2 transformation when you have a plus pi over 2. So we're going to take this thing to the left pi over 2 and redraw it. And this is our pi over 2 value, so it's going to start here if we move this guy over pi over 2 to the left, and this peak value here will go here. And notice that that is going to go there, and this guy will go about here. I'm just estimating this in here. And we're moving everything over pi over 2. And lo and behold, that red graph is not only the left pi over 2, but that's representing cosine x. So I think this is probably the easiest one to see how that transformation to the left produced for us a cosine x. So once again, just verifying that the sine of x plus pi over 2 is equal to cosine x. And the third way to do this is to do the addition of angles formula, or the addition of angles identity. And that is to rewrite the sine of alpha plus beta. And let me just write out that formula for those of you that maybe haven't seen this for a while. This is going to be sine alpha, sine beta. Boy, I sure messed that up, didn't I? It's been a while for me, too. So it's going to be sine alpha. Everybody out there saying, oh no, he's doing it wrong. Cosine beta, and then plus sine beta, or you could write the cosine alpha if you wanted to, and then cosine alpha. So we rotate the two angles in our formula. Now these have been proven before through the cosine alpha plus beta formula, and then we kind of move to this one as well. But anyway, let's work this out. So the sine, and this time we're going to use the sine of x plus pi over 2. And this is a real quick and easy one. This will be my alpha, this will be my beta. So we've got the sine of x times the cosine of pi over 2 plus the sine of pi over 2 times the cosine of x. And what's the key component here? And it's right here. This whole thing is 0. I just put a big 0 on that, so that's going to be 0 plus, and the sine of pi over 2 is 1 times the cosine x. So very quickly we can see that it's the same as the cosine of x. Sorry about messing up that formula at the beginning. It's been a while since I did that one. So there you go. We've got 3 different ways that we connect those concepts using the 4 quadrants, or using graphing, or using the addition of angles identity. I hope you enjoyed that, and I hope it helps.